Welcome to the presentation OpenMP target offloading for AMD GPUs. My name is Jan Patrick, or JP Lair, and I'm a software engineer in the AMD ROCm OpenMP GPU compiler and runtime team. I'm going to talk about OpenMP target offloading for AMD GPUs with different OpenMP features and new OpenMP runtime features for the current and upcoming AMD Instinct accelerators. As an example as to why you want to consider offloading parts of your application to the GPU, I have plotted the relative increase in bandwidth of one of our GPUs over the host CPU. This comparison uses an OpenMP version of the stream benchmark on the host CPU and an OpenMP target offloading version of Babel stream on the GPU. And as you can see from the plot, you get a nice benefit in bandwidth, and certain applications benefit similarly from moving parts or all of their computation to the GPU. In this talk, we first look at the ROCm software stack and its components in general. We then briefly introduce OpenMP target offloading with its main concepts. We then exemplify these concepts in a simple program to explain their meanings and take a closer look at what happens at runtime. We then extend this program with the OpenMP language feature called Unified Shared Memory and the differences of what happens at runtime. And finally, we take a closer look at the desired behavior and how the new zero copy feature of the AMD ROCm OpenMP implementation helps on the upcoming AMD MI300A APU. ROCm is AMD's open software stack that integrates components for both HPC and AI workloads. OpenMP and its GPU offloading capabilities are an integral part of the ROCm releases. OpenMP-based GPU offloading provides a standardized and portable way to access GPU compute resources and is therefore being adopted in ever greater fashion. AMD is invested in open source and open technology, and as such, all OpenMP GPU offloading components are open source. This slide shows kind of the organization of the whole ROCm stack. From developer tools and machine learning and AI development kits at the top, all the way down to the low-level ROCm language runtime and kernel driver, the ROCm stack offers a strong ecosystem to tackle all workloads. Now, in this presentation, I will focus on the OpenMP GPU runtime component of the stack, which is based on LLVM's target offload runtime. OpenMP is a standardized language, and target offload is the language feature that lets a user specify regions of the code to execute on an accelerator such as a GPU. OpenMP provides a standardized way for GPU programming as compared to HIP or CUDA, and directly integrates with the host languages C, C++, and Fortran. The fundamental keyword in OpenMP is the target keyword, which marks so-called target regions. These target regions are meant to be executed on an accelerator. In order for them to do meaningful work, a target region has a data environment, which explains how the target region needs access to data. This will be explained in more detail throughout this presentation. Finally, as a note, these target regions execute on one or multiple teams of threads to fully exploit the tremendous parallelism that today's GPUs offer. Now let's look at an example. Here we have a simple main function with a locally declared and heap allocated array. We have a compute loop that in this example does not do anything meaningful. And finally, we have a print loop that outputs all the values. if we are going to annotate the for loop with a Pragma OMP target, this will create a target region. And with the distribute parallel for, we tell the compiler to map the different iterations of that for loop to the different teams and threads in these teams. The map clause at the end defines the data environment this target region executes in. In this example, it mentions the vals array together with its size, going from 0 to 1024. The compiler and the runtime take care of the data being accessible on the GPU when the target region, a so-called kernel, is actually launched. So now on the previous slide, we simply had a map clause. Such a simple map clause defaults to a data mapping, meaning that a data transfer in both directions, or a to-from clause. To-from means that before the kernel, data is brought to the GPU, and after the kernel, that data is brought back to the host. As an example, if data needs to be only accessible for reading, a user could also map the data only to the device. For the rest of this presentation, and based on the explanations of the previous slide, you can think of this part of the program that's actually being executed on the GPU. So if we take another walkthrough of the actions required to execute the computation on the GPU, we can think of it as follows. On the right, we see GPU activity, and think of it as time moves from top to bottom. So first, we have a data transfer with the direction host to device. Once that data transfer has completed, the runtime can launch the kernel, meaning the actual computation of the values. When all the data has been computed, the runtime initiates another data transfer. This time, the direction is device to host. As one can see, depending on the computation and the amount of data involved in the transfers, the benefit from moving the computation to the GPU may be insignificant. Taking a more detailed look at the procedure and the technology involved. First, the code allocates memory on the host memory via the operating system allocators. Next, the map clause lets the runtime do the following. First, it will go through a variety of checks to see if the data was already present on the GPU. If that is not the case, it will allocate a device version of the vals array, here called devals, which is large enough to hold the 1024 integers. It will then initiate the copy via the PCIe or similar link that connects the host and the GPU. The kernel is launched and the results are computed. Once that is done, the runtime will copy the contents of the devals array back over the PCIe or similar link to the host and place them into the respective host memory address. For the best performance, programmers minimize transfers between host and device by placing map clauses at the beginning and ending of an application. As you can imagine, coming up with the best placement of these map clauses can be quite challenging. It can also become quite tedious for kernels that require a lot of different data to write the long lists of map clauses. Wouldn't it be great if the runtime could just take care of all of this? Thankfully, the OpenMP standard defines a feature that enables exactly this. It is called Unified Shared Memory, or for short, USM. I have used a different example here and gratefully reused the slide from Michael Clem with slight modifications. On the left, we see the original CPU code. Now, With the features of OpenMP we have seen so far, we can write a target region that looks like this. Note that for performance reasons, we map certain data only as to and other data only as from, basically removing a total of 2 unnecessary transfers. If we now want to make use of the USM feature, we add the pragma OMP requires unified shared memory in the beginning of all files, and are now able to not specify any map clauses for target regions. This makes it a lot less tedious to write target regions, as the data environment is automatically taken care of by the compiler, the runtime, and the driver. Note that for USM in the ROCm OpenMP compiler, the requires clause has to be present across the different source files. Looking at the USM mode in more detail, we find the following. As before, the code allocates some memory via the regular operating system provided allocation mechanism. Next, however, the map clause does not lead to a data copy across the PCIe or similar link. Instead, it maps the host pointer to the kernel, which means that it can also be omitted. When the kernel then executes and accesses that address, the access of a page address located on the system memory provokes a page migration from system memory to the HBM on the GPU. This migration is transparently handled by the driver, though the actual migration depends on the allocator used on the host. This behavior seems both convenient for the programmer and efficient for systems that share a single memory, like AMD's MI300A data center APU, as it involves zero copy. And it is indeed convenient and efficient. With the newest ROCm release, we introduce a zero copy runtime mode, which is specifically beneficial on the MI300A and its unified memory architecture. It removes the need for explicit transfers of data to the GPU and back. The MI300A has a single memory shared between the host and the GPU, and this mode is enabled transparently for the user without the need for special setup. It is, however, not limited to the MI300A, as other Instinct accelerators also support the features needed. As an important part, the zero copy runtime mode does not require any changes to existing applications. Remember that for OpenMP unified shared memory, the programmer had to insert the corresponding pragma in every source file. With zero copy mode, this is not required. Instead, default mode, meaning non-USM applications, can be compiled unchanged and yet execute in zero copy mode. Looking at the example from the beginning again here. The source code is unchanged and the map clause is present. Even though not shown here, the compiler flags are also unchanged. When the program is now executed in zero copy mode, the runtime, when encountering a map clause, will match the host pointer and redirect the pointer on the GPU to the address of that host pointer. This alleviates the need for data transfers. One exemption to this procedure is a special case handling of certain global allocations for some low-level technical reasons. For such allocations, the regular handling with a GPU memory allocation and data transfers is needed. Once the pointers are matched, the computation kernel is launched on the GPU and the same memory access technology is used as in unified shared memory, meaning that the access of a memory location from the GPU to that address may trigger a page fault and a subsequent page migration. In the case of an MI300A, however, the memory is unified and thus no memory migration is required. Visualizing what I just said for an MI300A APU here. The code first allocates memory with a regular call to the operating system allocator used. Next, the map clause is interpreted as with USM, meaning that it only passes a pointer to the pointer into the kernel. Finally, the kernel starts executing and the access to the page simply reads the value from the HBM that the original allocation was made at. Please note that in this example, a single socket is assumed. For configurations with more than one socket, page migration across socket boundaries may happen depending on where the original memory was allocated. We have seen there are a number of ways to achieve zero copy at runtime, and we thus want to summarize these possibilities. First, you compile your application normally for a given target architecture. In this example, for GFX 942. The columns of this table designate the programming mode, meaning if you use map clauses in your application, which we refer to as default mode, or if you use the OMP requires unified shared memory clause, which activates the USM mode. The lines in this table differentiate the machine or driver support for unified memory, with it being enabled in the first line and it being disabled in the second line. We can now see that for a default application, meaning one that uses maps, and for a USM mode application, the one that uses OMP requires unified shared memory, the runtime will perform zero copy. For a default application running with unified memory support disabled, the runtime will fall back to the regular execution with explicit copies between host and device. This mode is thus also available on MI300A. Finally, since an application that uses the OpenMP Unified Shared Memory clause requires unified memory support, the runtime will diagnose the missing support, issue an error, and abort execution. As you have probably seen by now, in an upcoming ROCm release, we are introducing an experimental compiler flag that allows you to compile any OpenMP program as if the programmer annotated every source file with the unified shared memory clause. This means that USM mode can be enabled for a program without the need for source code changes. In summary, zero copy mode is a ROCm OpenMP offload runtime feature that can provide performance improvements on APU systems. It enables execution of OpenMP default mode applications without explicit data transfers. Code generation does not change since it does not rely on special OpenMP features. Zero copy requires hardware or driver support. It is transparently enabled on supported devices via environment variable or driver level parameters. Unified shared memory, on the other hand, is a concept of the OpenMP language specification. It is designed to eliminate the need for manually specifying the data environment for target regions. The feature introduces a technical requirement which may change code generation slightly. USM also requires hardware or driver support. It can be enabled via manually adding the OMP requires unified shared memory pragma into source files, or with an experimental compiler flag that will be part of a future ROCm release. If you want to learn more about the OpenMP GPU compiler technology, consider attending the booth talk by my colleague Dhruva Chakrabarty at the AMD booth on November 15th. We also have a paper on how the compiler can optimize kernels for better performance in specific scenarios at the workshop for accelerator programming and directives. Finally, you can scan the QR code below to access the AMD ROCm website for more information about AMD's open software platform for GPU compute. Thank you very much for your attention. Please note our normal disclaimer that the information I presented may contain inaccuracies and is to be seen as is.